Electricity is another form of energy, and one that has become extremely important to modern society. Electric energy is essentially the energy associated with charged particles, such as electrons, protons, or ions. Why are charged particles different than neutral particles like neutrons and most compounds, though? They're different because charged particles follow the law of electric charges, which states that particles with like charges repel and opposite charges attract. So two electrons will push away from each other because they are both negative particles. But a cation and an anion will be attracted to each other because they have opposite charges. The force, whether attractive or repulsive, that one particle puts on another is its electric force. And then the area in which this force works is that particle's electric field. Any object that behaves according to the law of electric charges is charged and can then enact force on other charged objects or conduct or induce a charge onto uncharged objects. Individual atoms and most compounds in the natural state are neutral, meaning they have the same number of electrons and protons. This has to change for a substance to become charged. Since electrons are the most reactive particle in an atom, they are the ones that usually move to produce charged particles. If electrons are lost or gained by a substance, it becomes electrically charged. This can happen in three different ways: friction, conduction, and induction. When two objects rub together, friction resists their motion. It can also cause electrons to pass back and forth between the objects, making some parts of the objects positive and others negative. This is why you can stick a balloon to the wall by rubbing it to your hair, and why clothes sometimes stick together when they come out of the dryer. When those objects rub together, they develop charges and then behave according to the law of electric charges. Conduction and induction work when you already have a charged object. If a charged material touches an uncharged material, it can pass on electrons as they push away from the electrons around them and go towards the positive particles in the other material. An electric current will run across the country through a wire because the charged particles are being conducted through the metal as they try to find material with the opposite charge. Induction is similar, because you need at least one charged object, but it differs in that the objects don't touch and particles aren't actually passed back and forth. If a charged material goes near an uncharged material, its electric force can cause the electrons in the uncharged material to shift and create a charged area. Say, for example, you have a balloon that developed a charge after being rubbed on someone's head, or a sock that developed a charge while in the dryer. If that balloon or sock has a negative charge, it'll pull things with a positive charge towards it and push negative charges away. A neutral object, like your hair, has both positive and negative parts in it that cancel each other out normally. However, if you put the negatively charged balloon or sock near your hair, it pulls the positive particles in your hair towards it and pushes the negative ones away. Different parts of your hair now have different charges. The bigger the charge in the balloon, the stronger its electric force is, and the bigger its electric field is, so it can't induce a charge from further away. Lightning strikes the ground because the clouds have such a big charge that they induce the surface of the ground into having the opposite charge. So, to review, an object can become charged through friction, conduction, or induction. Electrons will keep moving until they contact a positively charged substance and balance their charge, but some materials let them move through easier than others. Substances that allow the free movement of electrons are called conductors. Metals are usually very good conductors because of the metallic bonds holding them together. If you recall, metallic bonds hold atoms together essentially by allowing electrons to flow freely from one atom to another. So, what difference does it make adding a few extra electrons? Since electrons are allowed to move around metals as they like, an electric current can easily move through them as well. Substances that limit the movement of electrons are called insulators. Materials made of covalently bonded compounds are usually good insulators. How much a substance opposes the flow of electrons, basically how good of an insulator it is called resistance. This is another physical property that can be used to describe a material. If you think of a normal wire, the copper inside is a good conductor because it has a low resistance. but the rubber coating has a high resistance, so it is a good insulator. Together, they allow the current to flow where you want it to, while keeping it contained inside the wire at the same time. Static electricity is different than current electricity. Most people will immediately think of rubbing a balloon on your head or walking around the rug in your socks. But those are not examples of static electricity. In both of those cases, friction is causing electrons to pass from one material to the other, creating a charge. Static means not moving or not changing. So if electrons are moving from one object to another and charges are changing, we are not dealing with static electricity. However, once you stop sliding across the rug or stop rubbing the balloon, you now have charged objects stuck with their charges. The charged particles have nowhere to go, so they are now static. Static electricity is an electric charge when electrons are not moving from one object to another. The clothes in the dryer rub together, they build up a charge, and when they stop moving, they stop passing electrons. They now stick together because of static electricity and the law of electric charges. A positive sock sticking to a negative shirt or a negative pant leg sticking to a positive leg. There is matter everywhere though, so objects don't hold on to static electricity forever. Eventually, the built-up electrons will find some place to go. The sudden jump of charged particles, the release of static electricity, is called electric discharge or static discharge. Electric discharge could be small and unnoticeable or large, loud, and bright. After you slide around the rug in your socks, the static charge could dissipate harmlessly as electrons pass to particles in the air. However, they could also jump from your hand to a friend or to a doorknob. In this case, you feel a zap, hear a slight snapping sound, and, if the lights are off, actually see a small bulge or flash. On a bigger scale, as clouds move and build, they pass electrons and static charge can build up. When these charges jump from a negative cloud to a positive cloud, or from a negative cloud to the positive ground, we see and hear lightning. The thunder you hear is just an amplified version of the snap you hear when you get zapped on a doorknob. The lightning you see, but hopefully don't feel, is the same as the little spark you saw on the doorknob or between the sock and pants as you pull them apart while folding laundry. Lightning is just a big example of static or electric discharge. No one will argue that being zapped by a doorknob after walking across the carpet and being struck by lightning is the same experience. So, even though all electric currents are just moving charged particles, they're not all the same. If moving currents of particles aren't always the same, though, how can we describe them and tell the difference? There are several different methods, but two of the fundamental ways are by describing the volume of particles moving and how much they want to move, which correlates to how many particles are moving and how fast they move. The first describes the electric current, the rate at which charged particles move past a certain point. In this case, current means basically the same thing as when you're describing running water. If someone squirts you with a squirt gun, the water is moving quickly, but there isn't much there, so it isn't going to knock you over or move you. However, if you step into a river, the water may be moving slower than the water in the squirt gun, but there's so much more of it moving that it will push you downstream if you don't hold on to something. There are more water molecules moving past you in the river than a squirt gun, so the river has a stronger current. In the case of an electric current, it is the number of charged particles moving past a certain point that decides how strong the current is. This is measured in amperes or amps. The wires outside bringing power from the power plant to your home are larger than the ones running through your house and are definitely larger than the ones used to charge a phone or MP3 player because they carry a larger current. The larger the wires are, the closer together the atoms inside them are, the more electrons can move through at once. Individual electrons don't usually move very fast, but they will start to move as soon as that option is made available. So your lights turn on quickly when you flip the switch. Electric currents can be a bit more versatile than rivers though. Some flow in just one direction, like rivers do, but some will alternate directions. When a current flows in only one direction, it is called a direct current, or DC. Currents powered by batteries are examples of direct currents. Particles flow out one end of the battery and in the other. When a current alternates in which direction it flows, is called an alternating current, or AC. The currents moving through the wires in your house are an example of an alternating current. Sometimes the current moves one way through your house, sometimes it turns around and goes the other. The direction alternates because the charge at the source, meaning the turbine at the power station, changes. The other important way to describe electricity is its voltage. Voltage describes the gradient between the positive and negative charges. The larger the gradient, the more energy the electric current will carry, and the faster its electrons will move. The term gradient refers to the difference between two values. There is a small gradient between 2 and 1, but a big gradient between 20 and 1. If you studied graphing and math and learned about slope, then this should be familiar. The slope of a graph is its gradient. If you haven't, you could also think of it as steepness. If you stood at the top of a flight of stairs and took one step, you go down about 8 inches, a small gradient. But if you took that step and the stairs weren't built yet, you'd fall 8 feet to the floor below. Taking one step forward and falling 8 feet down is a much steeper gradient than taking one step forward and falling 8 inches down. The bigger the gradient, the faster you fall. In the case of voltage, we're talking about the gradient between positive and negative charges. If there are a lot more negative particles in an area than positive ones, they really want to move. If the amount of positive and negative charged particles aren't quite as different, though, the particles are in much less of a rush and won't move as fast. The batteries in a remote control have a voltage of 1.5. Enough to make them move, but not enough to create a strong current, to power anything big, or to be very dangerous. The current running through your house, on the other hand, is 120 volts, so it can do a lot more and is much more dangerous. The voltage of lightning varies, but it can be up to 100 million volts, so in comparison to a AAA battery, it carries a lot more energy. It isn't necessarily the voltage that's dangerous, though. It's the volume of charged particles running through you, the ampage. However, currents with a high voltage usually also carry a high number of amps, so they are usually the more dangerous ones. Unlike electrical circuits, static electricity can't do work. A current has to be present, which means that there can't be a point in the system where electrons get stopped. They have to be able to flow consistently. A complete system or path through which electrons can flow without stopping is called a circuit. Anything with a switch or on-off button is just controlling whether the circuit flowing to that device is closed and functioning properly or open. When you flip the switch in the wall, you complete the circuit and allow the current to flow. When you flip it again, you break the circuit or open it and stop the flow of electricity. There are two main types of circuits, series circuits and parallel circuits. Series circuits are simple, single loops. Electrons all follow one path, and any loads, meaning devices using the electricity, follow in a series, one after the other. It's like cars going around a racetrack. There's only one path for them to follow. Parallel circuits are more complex loops. Electrons have multiple paths that they could follow. So if one is open, meaning broken, they can go a different way. This is more like roads around a city. If there's traffic or construction blocking the road, you can always take a detour. If a series circuit is broken, any device running on that circuit will stop functioning. The entire circuit is broken. If a parallel circuit breaks, one or two loads may be cut off, but electrons can find their way to the others. Part of the circuit may have broken, but the entire circuit probably hasn't. Your house is one large parallel circuit. If you break a circuit in the kitchen, you probably won't lose power to the whole house. The other branches of the circuit can still carry the current. Thus far, we have talked a lot about electricity, but haven't mentioned magnetism yet. So, what is a magnet? A magnet is any material that behaves a particular way when around certain metals. The traditional definition says that a magnet is anything that attracts iron, but they will attract a lot of other metals as well. Iron isn't particularly sticky. You can't glue paper together with a stick of iron like you can with a glue stick. So why are some metals attracted to it? The answer, similar to electricity, has to do with moving electrons. Electrons create an electric field because of their charge, but when electrons are moving, they also produce a magnetic field. All atoms have electrons producing magnetic fields, but the magnetic field of one electron is very weak. In magnets, the electrons are arranged in a way so that their respective magnetic fields add to each other, creating one large magnetic field. The electron motion that we're talking about here in particular is their spin. So while an electric current will allow you to generate a larger magnetic field, you don't need one to do so. The electrons just have to become organized based on their spin somehow. The more electrons and the more organized they are, the stronger the magnet will be. So large, dense samples of metal can be made into stronger magnets because they have more electrons. Why do magnets attract iron? They attract iron because, like most metals, the electrons in iron have a lot of freedom. So when a magnet comes near a piece of iron, it organizes the electrons in the iron and basically turns the iron into a temporary magnet. When things happen to the magnet that could disorganize the electrons, the magnetic field gets smaller. So dropping a magnet or increasing its temperature can weaken or demagnetize an object. A strong magnet has a large magnetic field, the area in which its magnetic force can work, and magnetic force is similar to electric force. However, instead of dealing with opposite charges as in electric force, here we are dealing with poles. Every magnet has two poles, a north and a south pole, on opposite sides of the magnet that have opposite magnetic forces. The north side of one magnet will repel the north side of another magnet, but attract the south side of the other magnet. And likewise, the south pole of one magnet will repel the south pole of another magnet, but attract the north. Finding the poles of a magnet can sometimes be tough, especially if the magnet is oddly shaped, or if it's a weak magnet, but they all have them. The poles of a magnet are designated by how they interact with other magnets, more than by what the electrons at that location are doing. The names north and south pole come from how the ends of the magnet interact with the biggest magnet around, the Earth itself. The moving metal within the Earth creates a massive magnetic field with a north and south pole, just like any other magnet. The magnetic poles are close to the geographic poles of the Earth, so the poles of other magnets are named based on how they interact with those poles. The pole of a magnet that is drawn towards Earth's magnetic pole that is closest to geographic north is called the North Pole, and the one drawn to geographic south is the South Pole. Since the North Pole of a magnet is attracted to the north of Earth, it actually has the opposite polarity. Earth's magnetic north is somewhere down in Antarctica. This could make things a bit confusing, so to make things easier, consider the North Pole of a magnet as the north-seeking pole, the part of the magnet drawn to geographic north. This is how compasses work. A compass is just a small, lightweight magnet allowed to spin freely. If there are no other magnets around, its north pole will seek Earth's magnetic pole closest to geographic north. Compasses, like any other kind of magnet, can be demagnetized or experience a reversal in polarity if they're handled too roughly or kept near other magnets. So it's important to be mindful of this when working with them. Even refrigerated magnets can lose their grip over time from being repeatedly dropped. Magnets on the fridge are considered permanent magnets. When they stick to the fridge, they turn part of the fridge into a temporary magnet. But there are other types of magnets that can actually be turned on and off on demand. Remember that we said anytime we have moving electrons, we'll also have a magnetic field. To make a magnet, we just need a way to organize those electrons. An electric current is a bunch of electrons all flowing together, so it meets both criteria. It has moving electrons, and they're organized. Essentially, this means that any wire, any circuit carrying an electric current, is also a magnet. When you close the circuit and allow the electrons to flow, the magnet is on. But when you open the circuit and the electrons stop flowing, the magnet stops working and is now off. How come you don't see paper clips flying across the room to stick to the wires and walls then? How large a magnet's field is depends on how many moving and organized electrons it has. So the wires in the wall aren't strong magnets because there just aren't enough electrons in any one spot. When people want to build this kind of magnet, they solve this problem by wrapping coils carrying an electric current into a tight bundle called a solenoid. That increases the strength of the magnetic field. The tighter they wrap it, the more moving electrons are squeezed into that same area, the stronger its magnetic field will be. If they increase the current by using wider wires and a higher voltage energy source, and add an iron core to the solenoid, they can make the magnet even stronger. Magnets made out of an electric current like this are called electromagnets. They take advantage of the interaction between electricity and magnetism together, called electromagnetism.